Hey everyone, let's dive right into this explainer. Have you ever actually stopped to think that literally every single thing around you, the chair you're sitting on, the screen you're looking at, even the very thoughts firing in your brain right now, is really just a series of microscopic collisions and electron transfers? Today, we are exploring the universe's ultimate instruction manual. We're going on a trip from the invisible particles bouncing around us every second, all the way up to the complex biological molecules that make up our very bodies.
To keep us on track and not get lost in the weeds, here is our roadmap. We're going to start with 1, the invisible dance of particles, then move on to 2, the rules of reactions, and check out 3, electrons, power, and rust. After that, we'll scale things up to 4, chemistry of our environment, and wrap it all up by looking inward at 5, the molecules of life. All right, let's get into it.
Okay, Section 1, the invisible dance of particles, kinetic theory and states of matter. So to really understand this stuff, we have to start small, like incredibly small, by looking at the chaotic, invisible dance of molecules happening in the air around you right this very second. Right at the core of all this is kinetic energy. According to the kinetic molecular theory, particles are just never truly still. They're constantly vibrating, sliding around, or just zooming past each other. And the physical state of any substance, whether we're talking about a solid block of ice, a glass of liquid water, or a cloud of water vapor, well, it's basically determined by a microscopic tug of war. It's this constant battle between kinetic energy, which wants to push everything apart, and intermolecular forces, which act like tiny little magnets trying to hold them rigidly together.
Now, think about what happens when you heat water. You'd probably expect that if you apply continuous heat, the temperature would just go straight up, right? But it actually doesn't. During a phase change, like melting at 0 degrees or boiling at 100 degrees Celsius, the temperature stays perfectly, completely constant. Why is that? Well, it's because all that thermal energy you're pumping into it is suddenly super busy breaking those molecular bonds, those tiny magnets we just talked about. Instead of raising the kinetic energy, it's literally a plateau in temperature while the entire chemical structure transforms. And hey, while we're on the topic of phase changes, I really want to clear up a super common point of confusion: evaporation versus boiling. So evaporation happens completely spontaneously, at literally any temperature. It's really just the high-energy molecules at the very surface of a liquid managing to finally break free and escape into the air. Boiling, on the other hand, is this massive bulk phenomenon. It only occurs at a very specific temperature, and that's when the internal vapor pressure of the liquid finally equals the atmospheric pressure pushing down on it from above. That's what allows those bubbles to form throughout the entire volume of the liquid, not just at the top.
Moving right along to Section 2, the rules of chemical reactions, kinetics and collision theory. So we know these particles are constantly moving around, but how do they actually interact to create the chemical changes we see all around us? Let's find out.
Well, for a chemical reaction to actually happen, it's not enough for particles to just, passively bump into each other. Collision theory tells us it's actually way more demanding than that. First off, they absolutely must physically collide. Second, they have to hit each other with the precise geometric orientation. Think of it kind of like two puzzle pieces snapping together. If they're backwards, nothing is going to happen. And finally, they need enough force to crest what chemists call the energy hill, or the activation energy. Without checking off all 3 of those boxes, the particles just bounce off each other totally harmlessly.
So, if we want to speed these reactions up, we basically have 2 main tools. We can crank up the temperature, which gives the particles more kinetic energy. This makes them move faster and hit harder, effectively brute forcing their way right over that energy hill. Or, and this is the elegant solution, we can use a catalyst. A catalyst is honestly brilliant because it doesn't add any energy at all. Instead, it provides a totally new, much lower energy pathway for the reaction to take place. In our own bodies, enzymes act as biological catalysts. They accelerate vital life processes by a staggering millionfold, and they do it without needing to raise our internal body temperature to boiling levels. Pretty amazing, right?
All right, on to Section 3, electrons, power, and rust, the mechanics of electrochemistry. Let's level this up. When these collisions result in the actual transfer of electrons, we enter a realm that governs everything from your smartphone battery to a decaying metal bridge. Basically, there are 2 main sides to the electrochemistry coin. First, you have the galvanic cell, like a hydrogen fuel cell. These are spontaneous. They happily and effortlessly convert stored chemical energy directly into electrical energy, which gives us clean power. But on the flip side, we have the electrolytic cell. Now, this one requires external electricity to force a non-spontaneous reaction to happen. And that is exactly how we do things like electroplate jewelry or purify metals on a massive industrial scale.
But this also perfectly illustrates the darker side of electrochemistry, which is corrosion. See, rust isn't just metal getting old. It's actually this tiny, incredibly destructive electrochemical cell forming right there on the surface of exposed iron. A tiny scratch becomes an anode where the iron just gives up its electrons. Then those electrons travel over to a cathodic spot, react with oxygen and moisture in the air, and boom, they create hydrated iron oxide. What's even worse is that real-world environmental factors, things like acid rain or dissolved carbon dioxide, act as electrolytes. They dramatically accelerate this whole destructive electrochemical dance.
And actually, speaking of acid rain, this brings us to a really crucial bridge in this explainer. We've seen the rules at the microscopic level, right? The collisions, the electron transfers. But what happens when these chemical reactions leak out into our atmosphere, our water, and our soil? How do these atomic rules scale up to impact the macro environment that we all share?
That brings us to Section 4, Chemistry of our environment, air, water, and soil. Because the very same principles we just talked about dictate the health of our planet's atmosphere and our own domestic water supply. The environment is basically just one giant chemistry beaker.
Just take your tap water, for instance. To make that safe to drink, municipalities use a really rigorous chemical sequence. First, aeration and sedimentation let all the heavy macroscopic particles just calmly settle to the bottom. Then comes coagulation. This is where chemicals like alum are added to physically clump all the tiny impurities together so they can be easily filtered out. And finally, the true chemical warfare, disinfection. By using halogens like chlorine or applying ozone, water treatment plants fatally disrupt the cell walls of harmful microbes. That's what renders the water completely safe for you and me to drink.
But as you might guess, human activity greatly complicates this really delicate environmental balance. Burning fossil fuels releases sulfur and nitrogen oxides straight into the air. These interact with atmospheric water to form nitric and sulfuric acids, literally causing acid rain that damages entire ecosystems. Similarly, car exhaust reacts under regular sunlight to brew up photochemical smog, and down on our soils, applying excess nitrogen fertilizers leads to agricultural runoff. That depletes the oxygen in our waterways and completely changes the chemical makeup of our aquatic habitats.
Which leads us to our final stop, Section 5, the molecules of life, organic chemistry and biochemistry. Let's zoom all the way back in and apply these principles to the single most complex machine in the known universe, the organic machinery running inside your own cells.
The absolute foundation of all life is organic chemistry. I know, it sounds a bit intimidating, but honestly, it's really just the chemistry of one incredibly special element, and that's carbon. Carbon is super unique because it can form 4 strong covalent bonds, which allows it to build these vast, intricate chain-forming skeletons. When they're bonded directly to hydrogen, these hydrocarbon frameworks become the highly versatile building blocks for literally everything living.
So the really crucial point here is how this incredibly versatile carbon backbone constructs 4 massive macromolecules in your body. First, you've got carbohydrates, which act as your immediate, highly combustible chemical fuel. Then there are proteins, which serve as the structural lumber for your tissues. And hey, remember those vital enzymes we talked about earlier? Yep, those are proteins too. Next up are lipids, or fats, which offer long-term energy storage and insulation. And finally, DNA and RNA. These serve as the ultimate biological hard drives, storing and translating the exact genetic blueprint that makes you, well, you. Every single physiological engine runs on this specific, delicate balance.
But here's the thing, those big macromolecules, they can't do it all alone. They desperately need micronutrients, specifically vitamins, which act as essential chemical cofactors. Without them, certain biological reactions just flat out stop. For example, a lack of vitamin C halts collagen production, which leads to scurvy. A simple deficiency in vitamin D doesn't just affect your bones. It actually alters brain chemistry, triggering profound systemic effects like intense fatigue and depression. And vitamin K? That is absolutely mandatory for synthesizing the proteins that clot your blood. It really is just a masterclass in chemical interdependence.
Ultimately, what you should really take away from this explainer is the profound interconnectedness of absolutely everything. From the evaporation of morning dew on the grass, to the slow rusting of an old car, right down to the DNA replicating inside your cells right this very second, we are entirely composed of the universe's most brilliant chemical equations, constantly reacting, breaking down, and reforming. So the next time you take a breath, or just drink a simple glass of water, ask yourself, what invisible, microscopic chemical dance is happening right now to make this exact moment possible?